All right, we'll go ahead and get started. So welcome, this is, okay, just needed to make sure my sound was on before welcome, this is Nerd-Sniped by Baseball. It is going over, I'll get to Nerd-Sniped in a second, but a postmortem on a side project that I did around exploring baseball lineup optimization using a bunch of really cool technology and algorithms. A little bit about me. I'm tech lead at Jernaya, and I am MC706 everywhere. I've written about this and a bunch of other topics on my personal website, mc706.io. So if you want to see the code for anything that was written here or anything like that, you'll be able to find it there. Nerd-Sniped. So for those who are not heavy XKCD readers, this is a reference that I hit a little too close to home while reading a few years ago. Overall, it says there's a type of brain that is easily disabled. If you show it an interesting problem, it involuntarily drops everything else to work on it. And here the author has led him to invent a new sport, nerd sniping. And he says, see that physicist across the road? And he shows this sign on an infinite grid of 1 ohm resistors. What's the resistance between these 2 points? And the physicist goes, interesting. Well, if you start, oh, wait, no, and then gets hit by a truck. And the author goes, yeah, or the person he's talking to, I will have no part in this. Come on, make a sign. It's fun. Physicists are 2 points. Mathematicians are 3. I found this personally almost like a personal attack. A number of times I've come up with an interesting problem and been unable to put it down. So the question that was posed was an ex-coworker of mine who coaches, very avid baseball coach for his son's Little League team, said, we should write an app to create an optimal lineup of baseball players so we could figure out how coaches can line up a lineup of baseball players so that they can score the most or however it is, which boils down to what is the optimal way to line up a given set of batters. And right there, I was done. So a little bit about me. I played a lot of baseball as a kid, and the basic strategy is you put your highest on-base hitters in the 1, 2, and 3 slots, and your biggest slugger in 4. And the idea generally is at the top of the first inning, you get as many people on base, and then you try to get someone to hit them all in. What the general strategy doesn't go over is what do you do with the other 5 slots on your lineup? And it doesn't really say much about it. There is a book that came out in 2014 called The Book. I guess as a play of doing things by the book. That goes into a bunch of observed statistics and strategies in baseball. So doing a pretty heavily statistical look on when someone lined up this way, on average, how did things turn out? And it does seem to support this strategy, but it also doesn't say that much about what to do with the rest of your lineup. So the first thing when approaching a big, scary problem like this is break it down into smaller ones. So given the question, what is the optimal way to line up a given set of batters, breaking it down into essentially 2 problems that are both slightly less hard. The first one is I need a way of comparing 2 lineups to see which is better. And the second problem is how do you find the best lineup given that the number of permutations of a 9-player lineup is 362,000 something. This problem gets a little harder when you talk about Little League lineups that can be up to 12 to 15 players, and 12 to 15 factorial are much, much bigger. So starting at the problem of comparing 2 lineups. In order to be able to say this is a best lineup, if you go through any like programming language and you have sort, you need a way that essentially takes 2 and says this one is above the other one. So given two lineups, which one is the better of the two? And then you can eventually find out a best. So off of the bat, I could think of two ways of approaching this problem. Simulate millions of baseball games with a particular lineup and take an average of all of their scores. So if having heavy hitters in the 1, 2, and 3 spot and sluggers in the 4 spot are good, on average, having that show up in a game should mean you, on average, have a higher score. And then over millions of simulations, you should come up with a good number that represents what that lineup represents as far as its average score. And the other way I could think of was probably figure out some clever math. I'm sure statistics has something to say about some of this. Based off of the description, you can tell that I probably went after the simulating games first. Quickly dropped into just a little bit of Python, built some data structures, talking about a player and some information about the player. So essentially decomposing a player into their statistics. And then essentially going through creating a game object, loading the players in that order, and iterating through simulating at-bats given their statistics, using their statistical batting averages as determining what are the chances that a particular at-bat outcome had. So essentially doing a weighted dice roll and simulating a baseball game. And then it gives me until 3 outs to an inning. And then I think here we had 7 innings to a game. So you run that, and then you get a score for that baseball game. If this runs relatively quickly, it's just a bunch of random number generation. If you loop over this a bunch of times, you will eventually get a running average of what a lineup was. So it worked, kind of, for some definition of work. At around 10,000 simulated games, there was still a pretty high standard deviation between inside of the set of games that were played, which meant that both of the bell curves, if you were comparing two baseball lineups, were both relatively flat, and it was often hard to say which one was better than another one, which meant that so it was very hard to compare two with at only doing 10,000 iterations. Moving up to 1 million iterations, the standard deviation began to drop, so the bell curves began to sharpen. And then taking their peaks was a little bit easier to see. But 1 million iterations of randomly generated numbers was somewhat expensive. So we threw in some multiprocessing, we threw in some threading, and essentially parallelized out the work as much as I could. And even with that, it was still taking on the order of minutes to simulate millions of games to just compare two lineups. So at 2 to 3 minutes per lineup, 9 factorial lineups would roughly take 1.4 years of compute time to find the best lineup. So the entire search space is still rather large here. But we tried it anyway. So luckily, the coworker who posed this question is currently employed at AWS. And running multiple year compute time calculations is something that probably was out of reach 10 years ago. And now we just boot a really big cluster and try to figure out. So using a mixture of free tier resources and some of the resources he has as an AWS employee for doing testing, we booted a cluster of machines and ran the script on them. It took around 8 hours, and we were able to search the entire search space for his son's baseball team. So we found an optimal lineup for his son's baseball team using this method. However, it would have cost us a pretty penny to actually implement, and that's actually not waiting 8 hours for an answer wasn't a great user experience, and it wouldn't be something we would want to do for an app. Doing compute years of work for any time a coach wanted to figure out their lineup was not a viable solution. So looking at that statistics hand wavy, there's probably a statistical way of figuring this out. After doing a little bit of research, we found expected value. Expected value is in probability theory, the expected value of a random out variable x, denoted E of x, is a generalization of the weighted average and can be used as in place of the arithmetic mean of a large number of independent realizations of x. That's a little scary. Here is the mathematical notation for expected value. And that was, at first glance, a whole lot of nope. Taking another look at it, though, it boils down to essentially you take the sum of all of the possible outcomes, each multiplied by the chances of that given outcome. So looking at some simple examples, if you had a game where you flip a coin, if you win, you get $1, else you lose $1. Intuitively, you can kind of tell that if a coin is 50-50, the expected value is going to be 0. The math shows that it is 0, and that you have a 50% of chance of winning times $1, so positive 50 cents, plus the chances that you lose 50% times minus $1, negative 50 cents. And you add them together, so 0. So if you had played an infinite number of these games, the vast majority of the time you will end up with not gaining or losing money. On a slightly more complicated example, the expected value of rolling a d6 dice is 3.5. You get that by adding up the chances of rolling a 1 times 1, the chances of rolling a 2 times 2, all the way up through 6. You add these all together and you get 3.5. And intuitively, what that means is if you had rolled an infinite number of dice, the average score you would get is 3.5. So there's a mathematical way of representing what an infinite number of simulations would have done. Looking at baseball lineups, it's a little bit more complicated than rolling a dice. It means that you have to calculate every possible outcome of every possible game, and then multiply that outcome of the game and the score by the chances that that series of outcomes was the final game. And then you sum up the results. And it's quite a lot different because it's not a continuous spectrum in that, like, you can't just say here's a series of events, because once you have 3 outs, you clear the bases, and then the game ends at some period of time. So the expected value is a little bit different because it's a discrete set, not a continuous set. So we gave up, and that's my talk. Except after doing a little bit more reading, and a few months later, I was doing some studying, and I got nerd-sniped again by the exact same problem. What I was studying was dynamic programming. So dynamic programming is both a mathematical optimization method and a computer programming method. It mainly has to deal with taking a big, complicated problem and breaking it down into simpler sub-problems in a recursive manner. And if you can recursively solve a problem by solving the optimal solutions for all of the sub-problems, that problem is considered to have an optimal substructure. And when a problem has optimal substructure, there are some things you can do with dynamic programming techniques to optimize for the solving of that problem. One of the big ones is memoization. So a real quick overcap of memoization. Fibonacci is one of your base examples of all of recursive programming. So you can take the Fibonacci number of n, and you can define it as the sum of the previous 2 Fibonacci numbers. And that's a really elegant way of essentially expressing your program as the mathematical definition of what Fibonacci is. The problem is when you define Fibonacci like this, the way you run Fibonacci it means that for every next step in the tree, you're producing 2 subtrees, which means that the amount of time Fibonacci of n takes in big O notation is O of 2 to the n. So when you call fib of 7, you call fib of 6 and fib of 5. But then when you call fib of 6, you also call fib of 5 and 4. But you're also calling fib of 5 and 4 over here. So you get a lot of repeated trees. And luckily, because these are all pure functions, there is a technique in dynamic programming called memoization that allows you to essentially say fib of 4 is going to be the same number no matter what. So if we have these repeated subtrees, you can eliminate all of the subtrees after calculating them once. In Python 3.9, actually, we got this cached decorator. This used to be the LRU cache decorator. This is just a partially applied one that makes it a little bit easier to read. But so I can add memoization to this Python function simply by decorating it with cached. What this will do is whenever I call Fibonacci, if it has previously calculated that number, it just returns out of memory. So it's trading a lot of time for a little bit of space. So the call tree for this will be fib of 7, fib of 6. It's just the left-hand side of this tree. So it ends up running in O of n space. So this, because Fibonacci has optimal substructure, and there's repeated work going on in these subtrees, using something like memoization allows you to cull out a large portion of those subtrees. So by being able to fit the problem into that optimal substructure, you can significantly increase the performance of your algorithm by cleverly eliminating work. So what does that look like for lineups? Well, if we reframe the thought of a baseball game and we think of a baseball game as one at-bat at a time. So a at-bat can be thought of as having close to an optimal substructure. So each at-bat is the same as a previous at-bat with slightly different statistics based on who's at-bat. And it is a forwarded version of the game. So when the first player is finished at their at-bat, all of the possible games that the second player could be batting in are based off of what the first player did at bat. So if they get a hit, they might be the second player might be playing in a game where there's a player on first and there's a runner on first and there's no outs. If they got an out, if they struck out or they got hit out, that player, the second player might be playing in a game with 1 out and nobody on base. So yeah, how the game state is different in each at-bat is dependent on the outcome of the previous at-bat. How often one game state occurs happens to be the chance of the at-bat of the previous batter producing that game state. So what does that mean? So if we look at the outcomes of an at-bat and how it changes the game. So if a player strikes out, we create a new game state where there's 1 additional out. If they walk, we advance the game state by adding a runner and advancing the bases. If they hit but get out, so like they ground out, we are going to say, for simplicity's sake, that they advance the bases by 1, but we also increase the number of outs. If you have a single, a double, a triple, if I can spell triple, or a home run, you advance the runners accordingly. You reset the bases after 3 outs, and you increment the inning. You keep track of the number of runners that get to home, increasing the score, and you keep track of the innings until a game is over. What you can then do is recursively define a baseball game as a series of at-bats. So this is actually a shockingly small amount of Python to do this. The first thing we did is I defined the game record. So this is the state of the game. It includes the inning. It includes the score. We have an inning score This is using a small technicality of Little League in that there's mercy rules on how many innings you can score how many runs you could score in a game or in an inning. That allows us to take a shortcut through our subtrees, because in theory, statistically, it's possible to have a game that never ends, which means that your program will never halt. So we're essentially adding an end stop there that prevents the halting problem, and saying that we're going to guarantee that all games end, no matter if it's statistically possible that they don't. We keep track of the outs, and then we keep track of who's on base. So in Python, I'm wrapping this in a data class with frozen equals true. What this does is, under the hood, it actually represents this as a tuple, and it hashes all of the fields for identity. So it means that if two game records have all of the same values, they are identical. They are identical in the eyes of Python, as opposed to if we were just using a class, identity is based on the address space. So if two games are the same, we can treat them the same because they hash the same. We then have our evaluate lineup function, which takes a tuple of players. This has to be a tuple in this case, because tuples are hashable in Python, lists are not. The player index, so essentially where are we in the that player in the lineup, and then the game state. So the previous game state. If we're starting with the game state, we are defaulting to none, and then the next line essentially gives us an empty game state. And then, so evaluate lineup will return a float, which is the expected value of that lineup. If the game that we're evaluating is complete, it just returns the current score of the game. And then our expected value function comes in this last step, where it takes the probability of a given outcome times the recursively called evaluate function with the same players, given the next player at bat, modulo the number of players so that it wraps back around to the beginning. And then we are applying the outcome map of the game. So this is how the outcome comes out. For the outcome and the probability of any player's outcome chances. So this is essentially saying, here's the chances that the outcome map here is strikeout, walk, hit out, hit, double, triple, home run. So any given player has equal or has some probability based off of their batting average and statistics of producing that next outcome. So recursively defined, this will search the entire search tree of every single. So for the first player, it's going to create 6 subtrees of, or 7 subtrees of all of the possible at-bat outcomes. For the next, for each of those, for each subsequent player. So it, without memoization, this function runs in 7 to the n, where n is the average number of at-bats in a baseball game, which is an absolute massive search space, which is why originally we didn't try this. Turns out, by making all of these arguments hashable and making the record use hash equality, you can use memoization. Here we're using the older LRU cache memoization decorator. And it turns out it works. This Python runs in a little under 30 seconds. It returns a single very, very precise value. And that value is deterministic. So given the same lineup, it always returns the same value. If I swap 2 positions in the lineup, it returns a new value, which now means that we have a very accurate way of getting a single answer for the expected value, which, according to the probability theory, is the outcome of the weighted average of all of the possible games you could have played. So we have a reasonable solution to our first problem. Unfortunately, we still have this 9 factorial to deal with. 30 seconds times 9 factorial is still 126 days of compute time. Not having an answer until after all of that is done is still not very efficient. It's still not a very good app. So we wanted to look for a way to find a good answer quickly, and maybe not a best answer, but maybe get to a better answer as we go. So this moves on to the second set of problems we were having, or problem 2. And for that, we started taking a look at genetic algorithms. So genetic algorithms in computer science and operations research is a meta-heuristic inspired by natural selection that belongs to a larger class of evolutionary algorithms. So essentially, you can create high-quality solutions by breeding other solutions together. So essentially, you're using biological processes of survival of the fittest to find a best answer or a better answer and continually improve over time. So you're not guaranteed to get a best answer right away, but it means that you can slowly get better and better and better answers as you go. This was not the first time I had played with genetic algorithms. Roughly a few years ago, I had written this little demo of genetic algorithms, which essentially takes all of these robots with mindless brains, and what they're trying to do is get to this green dot in the corner. And what it's doing is it's finding the bots that do the best and breeding their brains or their internal programming together so that you end up with these better and better generations of bots. So there's nothing here that the bots know about of getting to the green dot. Their internals are completely randomly generated. And instead, what we're doing is we're picking and interbreeding the bots that do the best to get better and better bots over time. So you can see that as they go, more and more of them will reach the green dot, and they will reach it faster. So here's a way of finding good solutions. It's, as you can see by the dots and the way they wave, we are not even close to the best solution, but it allows you to search a very large search space and find a good answer really quickly. The other interesting thing you can do, which is what are some of these visuals on the right, is start classifying the genomes and species of dots. And that allows you to essentially see how things improved over time, or how did things, what bots descend from other bots. So it allows you to start doing genealogies and classification of different algorithms. The other really interesting thing about genetic algorithms is, like survival of the fittest and evolution, if you start introducing barriers, they will eventually find a way to evolve around said barriers. So they are adaptive. So we could see that overall, our overall fitness dropped when we introduced some environmental factor that prevented them from doing what they were used to doing. But very quickly, they were able to find a way around that barrier. And over time, they will get better and better through this survival of the fittest means. So I had known of genetic algorithms. The other thing that I learned from this previous randomized bot project was that the visual heuristics of it were very important, because you don't arrive at the best answer like our previous our previous baseball optimizer was doing. Instead, you're getting good, progressively better ones. So allowing a user to see what progressively better means can help users also understand why things are getting better. And then seeing the genes themselves and how they interact will allow users to find a good answer and wait for a better answer. So given this, and given the previous example was a browser application that you can go to my GitHub and run in your browser and watch these little bots run around, I came up with the realization that I probably wanted to rebuild my genetic algorithm for baseball optimization in the browser. So rewriting it for the web. I gave a talk earlier today using Rust and WebAssembly to do high performance processing in the browser. I reused most of that work in taking my recursively defined lineup evaluator, writing it in Rust, and compiling it into WebAssembly so it can be called from JavaScript. I wrapped each of those WebAssembly modules in a web worker so it can be run as a pool of workers. I can then randomly generate a generation and display them using colors, because browsers are good with colors, and essentially throw them at the worker pool and have the worker pool respond with when they're done. And then I can then, as things are running, I can display the generations and statistics as we go. And I had a bunch of other plans there, and we'll see how it went. So when running in the web, it turned out Rust is far faster than Python. No one's surprised there. But Rust is, when running in WebAssembly, is also far faster than Python. The translated Rust version of that Python code run in roughly 5 to 10 seconds. Workers allowed me to thread that out. So if I have 20 people or 20 lineups in the generation, I could calculate them all at once. So I can do 20 at a time and very quickly start iterating through generations. With the expected value being a deterministic function, lineup values for a given lineup can be stored in indexed DB to cache comparison, so I don't need to double up on work. This, in the beginning, is not really a problem. When you're randomly searching 9 factorial, the chances you get a collision are very low. As it starts to run, you will find that you will get collisions on randomly generated lineups. So not redoing work you don't have to do is important. Going into it, there's a few levers that genetic algorithms give you. So generation size is how many are we considering at once. This mostly is limited by your compute power. Genetic algorithms have this concept of a champion, and that is the person or the lineup or the gene that did the best in the previous generation. We carry forward into the next generation without mutation, without breeding. We just say, you are the fittest, you get to survive. This prevents the degradation of the population as a whole, because it means that your maximum fitness is always at least that of your previous generation. So this prevents the gene pool from backsliding too far. The mutation rate, so after a generation has been interbred and fresh genes have been added, there's this concept of the mutation rate that allows random mutations to happen in genomes. In this case, we are randomly swapping there's a chance that we randomly swap 2 players in a lineup for any given gene. What this allows is if your gene pool starts to become stagnant, the mutations allow new traits to be introduced into your gene pool without tying things up too much. This is generally kept pretty low. But if you see over time, as your genetic algorithm is running, if the performance starts to degrade or become stagnant, you can up the mutation rate to introduce the chances that new powerful traits are introduced. And then we have the fresh gene percentage. So after some portion of time, interbreeding the best lineups helps, but so that the interbreeding section will always do a search for a local maxima. It'll look for, given what I have, how do I rearrange things to get better? What fresh genes do are they completely randomly generate a gene from scratch. And that allows you to search elsewhere in the space for other maxima. This is also an adjustable rate that you can then play back and forth with. So if it starts to stagnate, you can increase this to then, you've found a local maxima and you want to look for a more global maxima, you can increase your fresh gene percentage. So putting it all together, this is a screenshot of it running. So here we can see it had run 35 generations. I'll quickly go through this a little bit. Warning: it might not perform very well with Zoom. It's doing a ton of calculations under the hood, and it's going to probably start competing with Zoom for compute space on my computer. But we can click through a little bit. So the LMAP, which is just a real quick way of an explanation of what's going on. Hold up. Oops. I have the wrong link. Okay, so here I have my friend's Little League baseball team batting statistics preloaded in the normal version without the saved link. You have to input this yourself, but that's the whole point of the application. And then we hit this optimize lineup button. And what this does is, I'm going to pause it real quick. Okay, now that I'm not freezing. So what this has done is it has generated 20, so it spun up 20 web workers with 20 WebAssembly modules. It then ran the first generation, or generation 0, randomly generated 20 lineups, and then ran each of them through one of those workers. Those workers then came back with, here's the expected value of that lineup as a float. So these Little League games, and given the players, again, we'll get into some of the caveats of what this number means, but essentially they're expecting that we immediately begin to see there's a difference between a good lineup and a bad lineup. And on the low end of the spectrum, we can see that an expected value of 30 versus it looks like 37 is a pretty good value. What it then did was, you can see this this value here got carried over directly into the next generation. So this is our champion, and we said that we only wanted one champion right now. But then what it did was it interbred the top percentage of the best genes here. And you can see that like this red, purple, orange is already reflected here, and it also scored well. You'll see some other patterns, but as more and more generations run, you'll see it begins to, certain patterns begin to emerge that help the user heuristically say, hey, if we go, if player H, then player F, then player C, then player E bat in this order, we tend to get better scores. So after running many, so I've run hundreds or up to around 300 generations of this, this tends to converge on, you can see this nice bell curve on, not all BATUPs are created equally. The bell curve is slightly slanted to the right, in that it's not quite a normal curve. You have this 2-hump statistic. That is reflective of, we're not searching the whole space. We're essentially we're searching certain subtrees that seem to be more optimal than others. So the genetic algorithm is trying to produce more optimal lineups, which is why we have a concentration of good lineups in the top end. We can see the maximum fitness over time in this chart, and then the average fitness over time. So we can see that it started pretty low, but as it found good lineups, it interbred, and then over time we continue to get better, even 30 generations in. So that's the project. Again, I could run it, but then Zoom would probably crash because it's going to compete a ton for resources. All of the source code, it's all open source. You can look at the Rust, you can look at the Python, you can look at the Elm, the JavaScript, all of it's available open source on my GitLab account. It uses WASM-Pack, all of the configuration, how to run it, all of that should be documented here. So a few caveats. Baseball is a game of millions of variables and is by no means pure. The game that this algorithm is playing is baseball-like, and that's what it's trying to optimize. What I mean by baseball-like is there's no defense, there's no double plays, there's no weird pop fly rules or home run double or ground rule. So a lot of the rules of baseball don't play nicely into recursive algorithms, which the more of those rules you add, the harder it is to optimize this problem. So the game that this algorithm is playing is very much a one-sided game of baseball, given that everyone's playing by the same rules. So only given the batting statistics of the incoming batters, here are the best way to arrange them. It may not account for things like pinch hitters or things like that. So there's a bunch of things about baseball that it's not a perfect proxy for. The statistics that are used are outcome-based, which are different than how batting averages are kept in baseball. You can derive all of the statistics you need from the statistics that are kept in baseball, but like batting average and slugging percentage do not mean the same things here as they do on MLB.com. I've taken a look at writing a translating mechanism, but that was not nearly as fun or interesting as playing with genetic algorithms and WebAssembly. There is a caveat. It will still take the 126 days worth of compute time to find a global maximum. It does need to search the entire space to guarantee a global maximum. But the genetic algorithm is really good at finding local maximums quickly and giving a relative idea based on statistics how close you are to the best lineup. Okay, so lessons learned. The book, and after running this on a bunch of lineups and doing a bunch of research, the book and the general strategy of putting base hitters first and then a slugger in the fourth place actually does work. What this algorithm also explores is, it seems if you put a similar lineup of good hitters and a slugger at the end of your lineup, it also does better. So it does give some hints on what to do with the rest of your lineup. WebAssembly and web workers, again, we saw that Python algorithm took around 30 seconds. When I was running this in browser, I ran 20 of them in around 5 seconds. So the amount of performance you can get out of the browser and running it using WebAssembly, Rust, and web workers was amazing, and is absolutely something that people should look at if they're looking to squeeze extra performance out of the browser. Using genetic algorithms with visuals is really good for heuristic exploration. So being able to, over time, see what patterns emerge as the optimal patterns allows users themselves to make hypotheses and assumptions long before this is found an optimal solution. It can, if we ran this another dozen generations or so, you'll see the top 4 or 5 of them will probably have already converged on having people with high on-base percentage hits, and then it would probably move one of these sluggers with home run chances or good triple chances into the 4th slot. That's not guaranteed, but so I happen to know what the best lineup for this particular set of players is, and it is having this player B in that 4th slot. So it will find that, and it almost always finds it within a dozen generations. It finds some version of it within the first dozen or so generations. So, but allowing users to explore that themselves meant that they don't need to wait for the best answer. They can get a really good answer quickly. And then dynamic programming can make certain unapproachable problems a lot easier if you can frame them into that way of thinking. And that was really the second large nerd snipe for me here was how can I approach that problem in a way that I can optimize for. And that's all I have. So going through questions. Traditional wisdom holds you should put the player with the best QBA at the leadoff spot, player with the best slugging average in the 4th spot. Do your experiments bear that out, or have they produced evidence that? Okay, so right. So very early in my presentation, right, it does seem that it does vet that out. The traditional knowledge that, I mean, that's exactly what I heard, is you put your highest on base hitters in 1, 2, and 3, and your highest slugger in 4. It does prove that out. I've always seen that be the case. That is a little bit of a generalization of what this is doing, because this is actually looking at the individual players instead of trying to classify a player as a hitter or as a slugger. So there might be other things, like if they have a very low strikeout percentage, that change. So the way that, again, the way baseball statistics are kept, and this is doing calculations, don't quite always line up perfectly. So you have to do a little bit of translations on those statistics. But it does seem to test that out, and it does seem to have opinions on what to do with the rest of your lineup. Also heard it suggested it might be better assigned batters of. So that second one, where essentially what you do with the rest of your lineup, where you just organize it in decreasing order, this seems to suggest that is not the best way of doing it. That might prove, that might interplay with other things, that may play with other things as far as like other variables in baseball, but in a pure, again, in the pure game that was easy to optimize for, it seemed to not suggest that. The algorithm does not. So again, we're playing a game that is baseball-like. It was very hard to, once a batter is on base, see what the given statistics are. So this is so why the expected values are actually higher than you would normally see for baseball games is because it doesn't have things like certain games do, like batters have different averages against different pitchers. Like there's a bunch of different variables. A lot of that can't really be controlled for cleanly without eliminating entire rule sets of baseball. So the game it is playing does not include stolen bases. This is essentially, if you are having a home run derby of a baseball game, what is the best way to organize your batters in a home run derby is the game that it is most closely optimizing for. So it doesn't do stolen base attempts. There's probably a way of approaching that, but then you would have to keep a track of like on base statistics of runners and like that sort of thing. And normalizing, a lot of that has to be normalized against what the team you're playing against. So that was a little out of scope for what we were doing. I think there's probably a way to still approach that. And if you find a better way of doing it, the sources all open on GitHub. I'll await the pull request. Any other questions? I think we're basically at time anyway. Cool. Well, thank you for letting me nerd out about my nerd snipe on baseball and genetic algorithms.